Consider the initial value problem y prime is equals to lambda y, subject to the initial condition y at t equals to 0 is equals to y naught, where lambda is a real number. I'm going to derive the condition on h, where h is the step size for the absolute stability of Euler's method. So we are given that first order ODE. For the region of absolute stability, we denote it by gamma, and it is the set of values mu, such that the absolute value of f of mu is less than 1. That f of mu in some cases is referred to as the amplification factor. So we can write that as the absolute value of A is less than 1. For absolute stability, we'll be having that the absolute value of the amplification factor is less than 1. Now going on to look at Euler's method. If we are given a differential equation, the derivative of y with respect to t is equals to f of ty subject to the initial condition y at t naught is equals to y naught. And then for Euler's formula wave, yn plus 1 is equals to yn plus h multiplied by f of tn yn. So if we compare these two parts, this one and this one, we see that our f of ty is equals to lambda y. So from this expression, we can then obtain our f of tn yn. It will be lambda yn. And then we go on and substitute it into this formula here, so that we would have yn plus 1 is equals to yn plus h multiplied by lambda yn. What we can see there is yn is common. We can factor it out so that we have yn plus 1 is equals to 1 plus lambda multiplied by h multiplied by yn. But this 1 plus lambda multiplied by h is the one which is multiplying the yn, which we will now call the amplification factor. So we can write yn plus 1 is equals to a multiplied by yn, where the a there is the amplification factor, which is equals to 1 plus lambda multiplied by h. So for absolute stability, we say that that amplification factor is less than 1. So the absolute value of 1 plus lambda multiplied by h is less than 1. Then by using the definition of the absolute value, we can rewrite this inequality there as minus 1 greater than 1 plus lambda h, then less than 1. So that's the inequality that we are having. We can subtract 1 from both sides. Then we would have minus 1, it will give us a minus 2. Then this 1 minus 1, it will give us a 0. So we would have minus 2 is less than lambda h, then is less than 0. But in this case, we are looking for the expression for h. So we need to make h subject here. But to make h subject, we have to divide by the lambda. But when you are dealing with the inequalities, when we divide by a negative number, the sign changes. So we'd have to look at two cases there. If lambda is less than 0, if lambda is less than 0, then these two signs change. Then we would have minus 2 divided by lambda is greater than h, then greater than 0. Then the other option is if lambda is greater than 0. If lambda is greater than 0, when you divide by a number that is greater than 0, the signs do not change. So this expression here becomes minus 2 divided by lambda less than h less than 0. But when we looked at this equation in an earlier tutorial, we found its analytic solution. And we saw that the analytic solution is stable only if lambda is less than 1. If lambda is greater than 0, then the analytic solution itself is not stable. So we are less concerned about the numerical instability for this particular case, because the true solution will be unbounded if lambda is greater than 0. So we just look at the case where we have lambda being less than 0. So for lambda is less than 0, I can just go on and rewrite this expression here. So when I just rewrite it, is 0 is less than h is less than minus 2 divided by lambda. So this condition here for h, that's the condition for absolute stability of Euler's method. So that's our solution there.